Welcome. Welcome to the elements of machine learning. My name is Jilles Vreke, and I will be your guide into the wonderful world of machine learning for the next 7 or so weeks, after which Alexander Borjevsky will take over, because he knows much more about machine learning than I do, because machine learning is not really my core topic. It's just I happen to be the one teaching this course. Don't ask me how this came to be. Maybe in some break I will share this. Okay, so before I start, I want to create some evidence for myself. This is for my own pleasure. So let me put it in the middle. It's like this because, let's see. I apologize to everybody on Zoom, but I will just imagine that there's 30 people more in the room right now. Okay, good. Let's see how this looks in a few weeks. But at least right now I will have a memory of teaching. I think, well, this is the largest number of students I had as a lecturer in one room at one moment, especially given the last 2 years. Let's not talk about the last 2 years. Good. So let's see. The elements of machine learning. We're going to be talking about, well, the basic ingredients of machine learning. What makes machine learning tick? What is it? What is it good for? And so on and so forth. Before I start with exactly those things, I want to do a bit of expectation management. I'm going to show you a number of things that we're not going to be discussing. But to immediately remove the disappointment, the stuff that you will learn during the semester are the basic building blocks for the things that you're going to see. So I just took a few examples of recent years of humans being impressed and humans being disappointed. 2017, only 5 years ago. Lise Dock, the reigning world champion in Go, for a long, long time thought to be, well, completely impossible to be crunched by a computer because it requires intuition, deep thought, blah, blah, blah. Well, to quote him, let me move my window because Zoom is a little bit in the way. Sorry, Zoom. I don't know what to say, but I think I have to express my apologies first. I'm very sorry for the powerless display. Well, this is what he looks like during powerless display. This is the world's best player in Go, completely demolished by AlphaGo Zero, which learned how to play Go from scratch without any knowledge embedded, just from example games. Machine learning in 2017 at its finest. There was a barrier that we never thought was going to be crossed within, well, I don't know, a few hundred years or so. Then, yeah, well, board games, smart games, right? Who cares? I mean, computer scientists here, so we care more about, click. My clicker doesn't work. StarCraft, right? Now that's a game. That's a game. That's because you only have fog of war. You only see part of the game. You don't see the whole board, right? I mean, it's not just 2 players. It's not just black and white. But this is something, right? Well, yeah, this was 2019, and machine learning beat not necessarily the reigning world champion, and if I'm entirely honest, not entirely fairly either. It gets more information than the average player. However, it can beat almost any of you. I just allow myself a bit of slack in case we have the reigning world champion here in the room. Okay, this was just 3 years ago. Well, games, schmames, right? Who cares? We are scientists, or scientists in training, right? That's why you're studying a bachelor's of science, master's of science. So how about that? How about that? Is machine learning useful for that? Oops, there we are. This is just 2 years ago. At MIT, team used machine learning to screen through a metric, how do you say this in French, shitton of potential drugs that had already been screened for being safe for humans, to figure out if in those discarded drugs there was actually something useful. Was there a new antibiotic that we overlooked? And it found it. Now listen, and this is particularly cool because, well, we had the drug already. We could immediately start using it. And antibiotics is the one thing that we need pretty much the most. You may or may know this yet, but antibiotic resistance or antimicrobial resistance is going to be the biggest threat to human longevity, life, health in the upcoming decades, right? Bacteria are getting not so much smarter and smarter, but they can evade the drugs that we have easier and easier, by which even a minor infection becomes untreatable, and yeah, well, there you are. We're back basically in the Middle Ages, the Dark Ages. Minor infection will kill you. So thank you, machine learning, just 2 years ago. Pretty neat. Now, this is not very creative, is it? This is just sifting through molecules we humans already came up with that are supposedly useful. How about writing text, right? I mean, that is perhaps then the last bastion of human intelligence. Also 2 years ago, GPT-3 was introduced, the third in a series of large language models, learning from vast amounts of text, I mean, gathered from the internets. And well, this is an article that featured in The Guardian, a British newspaper, just 2 years ago, entirely written by GPT-3. Minor edits, editorial edits by the Guardian itself. So they gave it a prompt and okay, generate some text. If you read through this, well, let me put it differently. This is better written than many texts I've seen from, let me just say, students. I'm not going to qualify what level of students, right? But, and it just goes on and on. I mean, when you read it really closely, you will still see some, well, weird jumps, and it's not really coherent, and yeah. But you could say we'll fix this in the next few years or months, right? The advances, they go quicker and quicker. Personally, I'm very skeptical. I think this type of performance is what we're going to see, and right now we're only going to epsilon improve it until we make some big breakthroughs in causal inference. So just like we're not going to discuss large language models, we're also not going to discuss causality in this course. So such a pity. Perhaps some of you are here because you saw all these pretty pictures generated by DALL-E 2, by Imagine, by all these other models, right? Stable diffusion, for example. Maybe you're even running it on your own system. Really cool stuff. I have to admit, I'm really impressed. Right? Just type some words so you get a picture here. Leonardo da Vinci's early sketches of a cyborg. Pretty certain this was not just a lookup table, right? I don't think that da Vinci actually drew this, but it looks pretty convincing. All very, very cool stuff, and none of which we're going to actually do. So sad, so sad. Why? Well, you need to learn how to walk before you can run. And this is, well, running and stumbling. I could easily show you infinitely many fail cases of all these things. And perhaps over the next few weeks, I will now and then for my and your enjoyment. Good. Right now, I would like to start a bit more real on what we are going to do. I chose for this first lecture the title Bias and Variance. It used to be called Introduction, but I rather made it, well, what is the main point of this lecture, of today's lecture? And before we dive into this, I mean, okay, that's my name, that's Alexander's name, that's not so interesting. Let's talk about books. And also, again, expectation management, but now hopefully of the positive kind. Once upon a time, there was a professor here on campus called Thomas Lengauer who read this book. I said, okay, this is a cool book. People should know this. He was a bioinformatician, and he started a lecture series with the elements of statistical learning 1 and 2, where he discussed the first half and the second half of the book. This book is hardcore. This is a very good book. But frankly, this is not a book that I am willing to unleash on all of you just like that. Before I continue, let me actually show me a raise of hands. I mean, how many of you are bachelor students? I would not, friends do not let friends unleash this book onto bachelor students just like that. The other way around, how many of you are master students? It's the other half. It seems to be very 50-50. Anybody not a master student? Yeah, I was about to say, okay, Advait, I mean, that's, so Advait here in the first row, I mean, stand up, Advait. He's one of my 4, well, not elves, but one of the 4 TAs, teaching assistants for this course. So he will be helping us with preparing the assignments and giving you feedback, whatnot. The others are currently busy with other things. You will see them over the course. Good. Anyway, elements of statistical learning then was pretty hardcore. And at one moment, this book came out, An Introduction to Statistical Learning. And Thomas read this book like, okay, but this is good stuff. This is much better as an introductory course for statistical learning. And what used to be elements of statistical learning started to use this book. with that one as a backup. Right? But this is the pedigree. This is where it all stems from. Now, last year, edition 2 of the ISLR book came out. This is going to be our main text, an introduction to statistical learning with applications in R. Well, I don't care about R, so it's going to be applications in Python, right? Because R is great for statistics, but we're computer scientists, so we do Python. I hope that all of you agree this is a good choice. If not, get in your time machine, take the course a few years back. Okay? This is going to be the main book. So this one, I'm essentially going to be reading for you in the next few weeks, and Alexander then in the weeks after. We're going to be following this book almost step by step. This is by design, right? So if you're somebody who says, okay, I really come to a lecture to hear a lot more, this is not this type of lecture. I'm very sorry, right? For that, there's other lectures. I also lecture other lectures like that. This is a basic course I want to give a good introduction. So either you can attend the lectures, or you can read the book, or you can study the slides. All good, all fine and dandy. My goal is to make sure by this three-pronged approach that there's basically no way that you do not get in the end what was in this book, right? This I want to have in your head. You may ask, elements of machine learning, why statistical learning, right? I mean, come on, where's my machine? Fair enough, fair enough. When I took over this course a few years ago, first of all, there were only 30 of you, right? I haven't done a head count yet, but I mean, you multiply it somehow. Maybe this is because I changed the name. Maybe it's because something else. I don't know. Confounding factors. I have a big pile of machine learning books. I considered bringing them. And all of them are amazing, but not for a course like this. That book is really the best book to learn the basics. This is the best book to learn about regression, about classification. Dip your toes into non-parametric models. I mean, learn a bit about neural networks, and so on and so forth. All other books, they dive into the deep end much too quickly. And yeah, in the end, you might know how to operate things, but you don't know why they do what they do. In my lectures, I really care about intuition. In the end, I want you to know, like, okay, this is why it works, right? The pure mathematical details, that's for the assignments, right? That's where you can prove stuff. Deep understanding, you will not find them in the lectures so much. Initially, intuition. Because, also an often asked question, what is the difference between this course, EML, and the machine learning core lecture, which is taught in the summer semester? EML is a basic lecture by nature, right? You can also take it as an advanced lecture, but that's just a name game. Nice, cute little course, 6 credit points. Core ML, 9 credit points. That's a beast. So you have 2 lectures a week, I mean, assignment sheets, whatnot, right? I mean, it's a beast. That's where they go into really the mathematical details that I'm very happy to skip, right? Here you learn the intuition such that there you can jump into the deep end. That's how we design things. And to make sure that you can swim, you don't sink, this is the best book. So why is this book then also still on the webpage, right? And why is it linked? You can download the PDFs, right? I like reading from dead trees. Somehow the knowledge sort of, the osmosis is stronger for me. But if you prefer reading pixels, you can just download the PDFs. My advice to all of you, but especially those that want to dive a little bit deeper, first get the intuition from the book, from the lectures, from the slides, and then read up the corresponding chapter in this book. Because then you will really know how things tick. And my goal is that by giving you the right intuition, you can read this one. If you don't really care, okay, well, look, I don't really mind, except for a few small parts in the course, which will be clearly indicated, where we will be discussing the EML book and not the ISLR book, because ISLR just doesn't cover that. Huh? Good. Okay, so that was basically what I had in mind for the introduction. But let's get started. Unless there's questions, I'm very happy to answer them right now. No? Good. I see a few familiar faces, not so many. So most of you don't know me, but those of you who do also know that whenever I'm lecturing, I always drink club mate. And it's true, it's true. And the thing is, it's one of those weird, so you know these experiments by Pavlov, right? With the dogs and the bells and making them salivate and whatnot, right? I mean, I think I've turned myself into a Pavlovian dog a little bit, because I don't drink club mate when I'm not lecturing. And I just opened my first bottle in a few months and I took a sip like, yeah, lecture time. Okay, now let's see. Do you now work? Why don't you work? What is wrong with you? Yep. Yeah. This is annoying. Okay, no pointer for me. Then we just do it like this. Let's get started. Some applications of machine learning, right? If we're not trying to beat world champions, if we're not trying to discover new drugs and so on and so forth, right? Maybe we're going to tone it down a little bit. We're going to have a few more basic, bit more mundane examples, but again, you need to learn how to walk before you can run. Here we have some data set where for large population of males from the US, if I recall correctly, I mean 3,000 records, we have a number of things that we measured. Particularly, we're interested in how does their wage develop? How does their income develop? And well, we can use statistical or machine learning for that to gain some insight. First of all, we can even do something a bit more blunt. We can just simply plot it, just like I did over here. And you can see that there's clearly something going on between age and wage. So at first it goes up, and then it flattens out, and then, well, near the end it goes down again. Okay. The blue line, in this case, is just a stupid smoothed average. Works kind of well here, but what in the end we would like to be able to do near the end of the course, how can we measure and how can we model this relationship fine-grained so that we can make good predictions for individuals? Okay, but this is the first observation. If we now look at it slightly differently, if we look at really over year, not over age, then we say, hey, wait a second, there is clearly something going on. It's a small incline, right? But wage does increase year over year. Inflation correction and all that, right? So that also explains something, of course, between the older and the younger men, because if you started at a certain age and then inflation correction and so on and so forth. There's, of course, also a factor that is important, which is education. If you finished your PhD, you probably will start in a different type of job, make a different type of income than if you're just, fresh out of high school, right? Well, that you also see here. What does this mean? If we do want to predict wage, we should somehow take all three into account. And, well, how do you do this properly, right? This is not just taking a moving average or something, then we need something a bit smarter. We're going to discuss this in, chapter 3 of the book, and we follow the book. Right now, we're in chapter 1 and 2. Next week, we'll be in chapter 3, sorry. Good. So how can we predict things based on multiple features? Another example, because many of you are here, admit it or not, to get rich, right? Get rich or die trying, right? To quote the philosopher 50 Cent. That shows how old I am, I'm sorry. But, here we have stock market data. And some people claim to be able to read the stock market and make a lot of money out of it. In my observation, more like if you have a lot of money, then it's easier to make a lot of money with it. But getting it bootstrapped, that is difficult. Here we have 1,250 data points of, what was the level of, let's say, the height of the stock market on one day, next day, and so on and so forth. What can we learn from this, right, over these 4 years? First of all, if we just see what is now the distribution of did it go up or down, that's based on data from yesterday, this is essentially the same. You see, you have left and right in this figure. There's essentially no difference. No difference beyond just random noise. You really can't make any prediction. So that's a pity. How about data from yesterday and the day before? No, still nothing. How about yesterday, the day before, and the day before that? Still nothing. I'm sorry. So stock market is, perhaps it is completely chaotic. Or is it? Actually, it isn't. If we take into account very subtle signals in the right way, external input or trends over longer ranges of time, we can discover very subtle patterns which allow predictions of 60% accuracy. And 60% accuracy on the one hand, like, okay, well, what is that, right? I want 99.9. Yeah, sure, me too. However, in the investment market, anything above 50% means money. You just need to invest, wait a bit, it just amortizes out. 60% is a lot. Now, what is a bit unfortunate for all of you is that, well, of course, every stockbroker worth their salt knows about these patterns, so incorporates it, and hence, well, the market has adjusted for this, right? So We're going to be learning how to detect these more subtle patterns in, well, 1 week after. Just as a small aside, by the way, so besides that I drink Club Mate, one other thing that you should know about me is I tend to go off script because I think of things that I would like to share, and well, this is then one of them. As a researcher, wait, let me answer. Zoom, answer question out. As a researcher, you, besides doing research and trying to get this published, right, communicating, spreading the word, right, look how amazing my ideas was, right, I mean, bow for my intellect, that type of stuff. You're also supposed to evaluate other people's ideas, or specifically their papers. You're a reviewer, right? Typically, research papers only get published if 3 anonymous peers, right, from the, well, let's say community of researchers that study the same topic, more or less, if they said like, yeah, this is good stuff, that should be published, right? And every now and then, I get to read a paper where somebody claims to have broken the stock market. And unless, and this has never happened before, but unless I see a picture of the boat, of the yacht that they bought based on the ideas that they presented in the paper, it's an automatic reject, because I just don't buy it, right? I mean, that's, everybody's in the end in it for their own good. And if you have this great idea that breaks the stock market, then yeah, show me, right? Show me the money. Good. Anyway, and of course I don't automatically reject. I also page through it, but no, not good stuff. Okay, let's see. So this was the stock market data. Let's look at something a bit more useful, because there's probably also a number of bioinformaticians in the house. Can I get a raise of hands? Okay, well, you're well, semi-clustered. There's a cluster here with written. Okay, if you are. Hello, bioinformaticians. Not that this next example is not of interest of the others, but this one, as actually is a large part of this book, is specifically for you. So whoever was at the kickoff on Monday already noticed that I made the joke about Sven Rahman sequencing his own genome and then trying to analyze it. Well, that fits this course quite well. If so, because many of the examples have something to do with bioinformatics. How can we analyze large-scale, detailed, but also highly noisy data from the health and biosciences, and well, not just predict whether somebody is likely to get or develop a horrible disease or not, or can we figure out how certain proteins or whatever, I mean, the mechanisms, how they interact, right? It's not just predicting, it's not just clustering, it's gaining insight. And bioinformatics is one of my favorite fields of application of the stuff that we develop in my group. Not the only one. I mean, I'm based at CISPA Helmholtz Center for Information Security, so cybersecurity. There's probably also plenty of cybersecurity students here in the house. Also a cool application area, but the biohealth domain that typically, I mean, triggers pretty much everybody. Here we have an example that, well, I would not particularly call big data. We have here 64 cell lines. So basically, let's say breeds of bacteria, right? For those that, and well, those are more or less related to one another, right? That's how you can see it. And for each of those, we can sequence their DNA or do some measurements, right? So here we have almost 7,000 gene expressions for each of the 64 cell lines. Let's call it bacteria for now. Now, one of the questions is, okay, how do they relate? Can we somehow group these beasties by how their gene expressions work, right? Or how can we do it by how their gene sequencing looks, or I mean, how they taste, and so on and so forth, right? How can we group them? Because maybe that gains the insight. Well, that we have done here. We've done principal component analysis, which we'll discuss in, I think it will be actually Alexander who discusses this. So this will be lecture 8, give or take. So we have here our own coordinate system, Z, so the principal components. As you can see, well, this looks quite clustered, right? So the green, the yellow thingies at the bottom, they seem to be a family of some kind. And then, well, here we have this relatively dense blob of blue things, right? So the colors are the result of some analysis method, right? Don't believe the colors. Here we have these orange ones, yeah, whatever, right? They're a bit strange. Let's call them outliers. And then these green ones, they don't really seem to belong to the blue ones. Looks good, looks good. Or is it? I mean, that's how many clusters do we actually have here? Because if you stare at it, the blue one, I can easily break into 2, right? You have the left-hand side and the right-hand side, or maybe even to 3 parts. And the green one, I can also easily break into 2 more parts. I mean, basically, almost any number between 1 up till n is the number of data points typically, can make sense. Which one is it? How to determine that? That is a very difficult question if you're in an unsupervised setting where we're not trying to predict as well as possible, but we're just trying to describe the data. Nobody is telling us whether we're right or wrong. We just have to go to the bioinformatician and say, okay, what do you think of it? And more often than not, they'll say like, bah. Because in this particular case, I now color and label them according to, well, these are actually cancer cells. These are not bacteria, these are cancer cell types. So the shapes now correspond to, well, which type of cancer we're looking at. And all of a sudden, this beautiful cluster we had at the bottom, the green is a bit mixed. The blue one is just a mess, right? I mean, that includes many different things. And now the real problem is staring us right in the face, or in the eyes, whatever. Is this a good or a bad result? Could it be that the gray, the gray, the orange at the top, and the blue, are they perhaps more related than we thought? Maybe they're different cancer types, but actually they're very similar. Or maybe the method just messed up. Nobody knows. This is called exploratory data analysis, trying to figure out what are hidden important structures in the data that we do need to know about. Because if we do find that those are all related cancer types, well, perhaps we can come up with one treatment. If they're really different, well, then probably we need different ones, and so on and so forth. Exploratory data analysis. This we do, I think, after the Christmas break. Good. So just as a few examples of different data types, different tasks that we might be interested in. Any questions so far? Any disappointments? I mean, 2 people left, so they were clearly disappointed, or they had other things to do. So it's good that I already took the picture, right? And they're still on my picture. So let's get started now for real. So chapter 2. What we just saw was chapter 1, essentially, of the book, right? Very high level overview. One of the running examples I'll be using in the first few lectures is the advertising data set. It's a little bit dated because, well, it is data of given how much investments in certain branches of advertising, certain media, how much did our sales, well, how much sales did it produce, I mean, that lead to? What are the 3 different media that they consider? Well, advertisements on TV. I'm not even going to bother if anybody watches TV or ads on TV anymore, right? But, radio. I mean, you probably don't even know what radio is, right? And it's like a streaming, but then with the box. Newspaper. It's I don't know, like a news web page, but then printed. That doesn't really matter, right? I mean, we have 3 different media, which may or may not be as effective. These inputs we often call the predictors. Based on this data, investments in these 3 media, it's easily measurable, right? These are our predictors. We call them X1 up till, right, XP. We typically have P predictors. You can also call the input variables, features, whatever, right? I mean, in different books, different names, but they all mean the same thing. And what we're trying to do here, we're trying to predict something. We're trying to predict why. Why is the usual suspect? It's the output variable. How much sales do we gather, right? I mean, that's how strongly, I mean, or how bad does the disease get, right? Stuff like this. We also call this the response variable or the dependent variable, depending which book you pick up. I will try my best to stick to predictors and output variable or target variable. That's what I often use. Please bear with me if I now and then use different words. If I truly confuse you, let me know. In general, what we're now doing, and this is already the first and perhaps the most important lesson within the whole game of machine learning, we're always making assumptions about how the world works. Even if they look very benign, these are very fundamental. Because by saying that, hey, we're interested in X1, 2, 3, and Y is the output variable, we are implicitly already assuming that there exists some mechanism, f of x, that produces y, right? Actually, this equal sign over here, that should be more a sign operator, right, rather than a pure equals. It's not just this mechanism of x, but there's also some noise, right? Sometimes weird stuff happens. Maybe the noise is independent of x, maybe it's inside the function, maybe it's, we assume some form. the type of form that we assume, like here, f of x plus some noise, which is not part of the function, that excludes a large part of possible relationships, which may actually include the real one. And well, I don't really have to spell out what's going to happen if the real one is excluded, and we're just going to pretend that it's in the one that we assume, right? Yeah, we're going to get some answer, but an answer that may be just nonsense. And it may work well in certain cases, but in general, nah. So, but this is the form that we in general assume. It's one of the dirty little secrets in machine learning. There is some mechanism, f of x, and some random additive noise with zero mean. For those of you who are bored, why zero mean? Think about it. Oops. Yeah, there we are. Good. Let's see. We go over the three x's, x1, 2, 3. Start with TV. We plot based on investments. That is, I think, in thousands of dollars on the x-axis, and then the number of sales on the y-axis. And maybe I should not have immediately shown the blue line, and I should have asked, okay, well, what would you guess is the relationship? Yeah, probably something like the blue line. Maybe a bit more steep. Maybe actually it should not be a line so much. Maybe it should be more like something that goes like this, right? Something logarithmic. But anyway, looks like a pretty decent line, right? If you would need to fit a line to this data, this looks good. Next, radio. Well, that looks like a little bit more of a mess, right? There's still some relationship between how much we advertise on radio and what is going to happen, but it's much less clean than for TV. This would be the line. Newspaper. Okay, should we invest in newspaper, or is this just a waste of money? Which is a very good question, and not just in this particular case, but in general. These are types of questions that you do get, not just in science, but in industry, as we academics call it, right? I mean, nothing to do with factories, but should we invest, yes or no, on this data? Now, if you do your analysis here, then there is a slight positive correlation. So it is not perhaps as effective as on TV, and the ads, but at the same time, you still drive sales up a bit. If it would be completely flat, then it would be easy, right? Okay, don't invest. This is nonsense. Now, of course, the question is, had we not invested in newspaper, had those people not already bought our stuff because, well, either they just wanted to, regardless, they needed to, they had seen the ad on TV, right? So all sorts of confounding effects. So this also brings us again to what we saw with the wage data. We should not analyze this just purely independently, one by one, like we do here. We should actually do this jointly. But we don't know how yet. We don't know how yet. Well, we'll only learn this next week or the week after. Another example, that's the wage data again. Whereas in the previous, you could indeed say, okay, this is linear with a lot of noise. And let's look again, right? Linear-ish with a lot of noise. I mean, so the radio maybe it fans out a little bit. The TV is made of a plume, but linear seems to fit. Now on this data, number of years of education versus income, yeah, you could say this is linear, but this is more like an S-shaped type of function, right? Which also kind of makes sense, that the first years of education, you don't automatically make a lot more money. You first need to earn your spurs. And same thing at the end, right? I mean, if you really have followed all possible courses here at Saarland Informatics campus, or you took, well, enough to finish your master's, you will know a bit more, but your salary is not going to explode all of a sudden. Now, so this is a data set that we generated ourselves. It's a bit sneaky, but fine. And we know what is the true functional relationship here. This is S-shaped. So we know what should be found. But in practice, of course, well, poor machine still needs to find it. It needs to be estimated what this relationship is. So this is the true one, if I'm not mistaken. And as you can see, well, if the true one, or let it be the estimated one, it doesn't matter for the sake of the story, is not perfect. Because noise, there is additional noise sprinkled on top, right? And you can imagine that if I would draw a line, chickadee, 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 go through all the points, it would perfectly predict this data, but it would probably not generalize at all. because only for these data points it's perfect, but one other data point, and then you will see, right, that you make this weird dip to avoid, to connect 2 points, and then now this one gets sampled. So it's better to get the one that fits overall best. How do we measure this? How do we make sure that we find the line, that curve, that goes through these points in the right way? Well, what we do is we measure how wrong is it? How do we measure that? By drawing lines from the predicted line, from the blue one, to the points we want to predict. This is essentially what we do, all these black lines. And what we ideally want is that blue line with the minimum, well, number of minimum lengths of black lines. That's essentially what it comes down to. Should we just sum these black lines plainly? You'll see this in a few slides from now. The answer is no. No, we should actually take the square of these black lines. Basically, the moment that they're long, then we penalize it much more, right? So we don't want a blue line that forgets about a few points, right? By just making completely arbitrary wrong decisions. So squared is better in this particular case. Good. And now, if I give you a whole bunch of possible blue lines, you have already the intuition of how to choose which one is best. We haven't formalized it yet, but we'll get there. So why estimate f again? Why estimate this function at all? It's a bit of a repetition here, but I mean, why? Well, the inputs are available. That's why they're called predictors. We want to predict something based on it, right? The output is not, but it's desired. We want it. We would like to know if we increase spending here, does this go up? If I have a headache, should I take an aspirin? Questions like that, right? But if I want to get a better grade for EML, should I study harder? Maybe, maybe not. Depends on how much you already know. So what we want is this, right? So x we have, the true f we don't have. That's what we want to estimate, and then that spits out an estimated value for y, and that estimated value should be as close as possible. This is the general form of it. And if we're just interested in prediction, and in many, many cases we are, effectively, I could even say that in almost all of machine learning, the history of machine learning, nobody gives a rat's ass about what is the shape, what is the form of this f hat. What I mean by shape or form is like, is it linear, is it cubic, is it whatever-ish, is it a deep neural network with 15 million gazillion parameters? I don't care, as long as it predicts well. That's what I care about, right? A little bit in the line of thinking that we have so I just for the record, I do not believe in self-driving cars. We're not going to see properly self-driving cars for a long time to come, right? That yesterday's announcement that Ford and Volkswagen, that they canceled their big multi-billion project in self-driving, shocked. I was shocked. I was devastated. I also don't have stocks in Tesla. But then again, perhaps I should have done this a few years ago and I still would have been more rich. I don't know. Anyway, I don't believe in self-driving cars. Why not? Because all this stuff is based on deep learning in the end, and deep learning is fantastic. You can do really cool stuff with it. We saw some examples at the beginning. But yeah, then you have your f hat with 15 million gazillion parameters, and you have no idea what it's doing. When will it work? When won't it work? Is it cheating or not? And yeah, that's exactly the settings. Well, that's exactly the things that I care about. If you want to apply the machine learning method in a healthcare setting, and you have to tell them like, yeah, well, it works on my training data, right? I mean, that's okay, but can you give guarantees? Well, it works on the training data. Yeah, no, right? No, no clinical practitioner will say yes, and no, car approval? Is it authority? Road approval authority. I mean, worth their salt will also allow self-driving car for which you can't give any guarantees onto the road. Now, guarantees do not necessarily mean understanding the form of f hat, but that does go hand in hand. The more we understand about f hat, the easier it becomes to give guarantees. When does it work? When doesn't it work? And so on and so forth. Okay, so let's forget my rant about self-driving cars. For example, here, blood profile is input, and okay, so severe reaction. Now, if we think about such an f hat, this f hat is automatically not always going to be correct. Let's especially if there's noise in the system, it cannot always be correct, because then it would be modeling noise, and that is actually bad. So we have to think about goodness and badness when we're learning a function to predict in terms of error that is avoidable and error that is unavoidable. Or in other words, reducible error and irreducible error. Where irreducible error is error inherent to the system, that is really the noise that you don't want to model. Maybe the shape of the noise, but not the actual values. Now, for a fixed input x and a fixed function f, we can actually write this out. This should be f hat, by the way. But, actually, no. The expected difference between the true value y and predicted value y, if we take the square of it, we can break it down into, well, we can define it as this, and then we can break it down into this. What do we have here? This is the expectation of what the function is going to say, plus the error, minus what, well, the predicted function is going to say. And then we have here, if we break this down further, we can pull out this epsilon here, the irreducible noise, which just becomes the variance. That is really the noise inherent in the system. So this is the reducible error. This is the irreducible error. Yeah, expectation of all possible training sets. We're really thinking about big numbers. Then we have here reducible error, irreducible error. This essentially shows that whenever you have a learning system that gives a performance that is too good to be true, errors that are so low that you think, okay, what is going on here? Oh my God, I mean, should you pop open a beer, or should you, well, go back to the drawing board? It's your party, but I would go back to the drawing board, because you should not be able to reduce this irreducible error. The moment that your system starts to learn that, at the very end of the course, we will be discussing neural networks. And over the next few weeks, I will be bashing neural networks, because that's what I do. Doesn't mean that I don't love them, right? But that's sometimes a bit of tough love is important. Because you can easily show that if you take some data set with some true labels, right? And where we know that there is some relationship, because we generated it ourselves, or because just it's there, right? Then you can learn a deep neural network, just you can learn all sorts of other methods that we will discuss. And you can learn the dependency between the two. And that is good, because then it apparently learns this f hat. Good job. Now, if we just randomly permute only the labels, so the data stays the same, right? But the labels, so there's no connection between labels and input anymore, then, well, we should not be able to learn anything. If you have a rich enough class of functions that you optimize over, like you do in deep learning, you will find, and I can guarantee it, if you haven't done it, you haven't done your homework, a deep neural network that will get a 0 error. And it will be happy. Look how well I can predict. There is nothing to be predicted. So that should be a word of warning, right? And as well as like, oh my God, that is amazing. It does mean that if there is something to be learned, it can learn it. Just give it enough data, enough time, it will learn it, right? I mean, that you don't have to do all the hard work. Okay, can it learn it? How should it learn? Blah. No, it will learn it. But the problem is that if there is nothing, it will also learn it. And how to separate those two, yeah, that's what, amongst others, Advait is working on. This is what I just said. Good. I'm going to continue for a few more slides, then we take a short break. So this was prediction. There's also another reason why we could be wishing to estimate f. Because that, if we want to gain some insight into the data, we want to do inference. So now we are really explicitly interested in the relationship between input and output. What form does it take? I mean, what happens if we do this, and so on and so forth? How many groups of bacteria are there? Right? Going back to the example. So, for example, you have then questions. I mean, which predictors are actually associated to the output? Right? Often, like again with the gene expression data, I mean, 6,830. Suppose that we now want to predict something. Are all of those going to be relevant? Probably not. In most cases, you only need a handful of them. Which ones are those? Right? It's inference. What is the relationship between the response and each predictor? Well, sometimes there's a joint effect, sometimes they're individual. And how can we tease that out? Often, it is joined. It's not just 1 and 2, like in the advertising example, right? I hope that nobody here in the room believes that, well, it's completely independent. right? That if you drive up, if you invest massively in TV ads, then somehow people who even never see TV will run into somebody who saw it and spoke about it, and there's some trickle down. There's always interplays. So often depends on other predictors. What form does it take? Is this relationship linear? Is this a straight line like we saw, or what we assumed? We just drew a straight line. Or is it a squiggly line? How squiggly? Which squiggly line? Is it multiple lines? Okay. Often, in my experience, this is different than what you thought at the beginning. I've been in many, let's say, collaborations where people are like, no, it's not going to be linear. Never. Or like, no, it's absolutely not linear. It's absolutely like this really mega complex function. Like, So the best thing that I can, the second most important lesson, do not blindly trust your domain expert. Never, right? Always look at the data first. Inspect it, right? Question everything and anything, right? Assumptions, excuse my French, are the mother of all fuck-ups. One of my favorite expressions, because it's true, right? Assume something, nature is going to slap you in the face like, and there you are, right? Your method doesn't work, and so on and so forth. For the advertising data, which media do contribute to sales? Which one generate the biggest boost? Would a combined campaign be better than an individual campaign? I don't know. But, and then, so even though I like these inference questions personally most, because somehow for me, it feels like they're harder. In just predicting something, trying to find a better function that fits better, I don't know. There's people, especially that are very good at math, that are simply better at that than me. But these inference types questions, those are the ones that are fuzzy. I mean, how do you even define them? And if you define them badly, then you'll never find a good answer. So you really need to understand the problem, possible solutions, then think algorithmically, how can we even solve this? Is this optimizable? And so on and so forth. So picking really the right problems and trying to bring some real insight, this is what makes my heart beat faster. So that's why I like inference. However, very often, inference and prediction go hand in hand. Whereas, for example, then Tesla's self-driving system is completely vision-based and completely, well, opaque, right? Deep learning, whatnot, there's no way of telling it. Yeah, you would like to gain a little bit more insight. Would a neurosymbolic approach, where perhaps we use neural approaches to do the low-level vision things, like recognizing if there's objects and stuff, and then we would have a more high-level reasoning engine, like, okay, well, if this and this happens, then if, let's say, a ball comes bouncing toward the road, should you keep on speeding or should you slow down? Well, in the training data, probably there's not been that many balls with kids running after them, but if you are a reasonable driver, or actually if you're allowed on the road, then I hope that when you see a ball bouncing towards the road, you slow down, because big chance that there's a kid coming, right? Whether this is a young kid or an adult kid, doesn't really matter. You don't want to hit them. You want to be able to reason about, does your model do this? Good. Inference and prediction go hand in hand. So a very interpretable, translucent model is not always the best at prediction, and the other way around. So there's always a bit of a trade-off. And very often, as we also see later in the course, people don't really know what they want. They claim that they want just prediction or just inference, but in the end, they actually care also quite a bit about the rest. So again, don't trust your domain expert. Don't trust yourself even. The trade-off is that simple models, let's say linear regression, which we'll see next week, are super easily interpretable. It's just fitting a straight line. But yeah, if the line should not be straight, they're not that great. Flexible models, like deep learning, super wiggly lines, can fit anything. Yeah, what did they actually fit? Good. Right after the break, I'm going to be showing you this slide, how to estimate F. But that is going to be in 10 minutes from now. So let's take a short break. Let's take 10 minutes of breather, be it inside or outside, your call, and then we continue. So in the break, I was asked to turn up the volume of the microphone. I did, and I don't hear any big complaints from Zoom, because I remember from previous years, then if I did this, then there it was horrible. So no complaints yet. And I hope it's, I don't know where the people were sitting who asked for this, but there you are, Sasha. Is this better? Yes? Good. Okay. Thanks for letting me know. Good. Okay, then let's continue where we were. Come on, you were working like a second ago. I'm gonna do it by hand again. Okay, back to estimation. How do we estimate a function f? Well, the general setup in machine learning is that we have training data over observations, but we happen to know the right answer. It's really sort of a teacher-student, student-teacher type of setup. We typically say that we have n observations. We have a data set D containing n observations, which are tuples. So this is observation 1, x1, however many variables x1 may consist, maybe one, maybe many, right? Who cares? And then y1, the corresponding output. And what we now want to have is some function f hat that for any of these pairs, well, the predicted f is approximately the right value. Approximately is where we wish away the irreducible error. There's essentially two important classes of methods that you should know about. And these classes of methods, they are formally defined as here and there, but they kind of run into one another. The first class is those of parametric models or methods. And the other one is a non-parametric. Let's first go to parametric. In parametric methods or models, we assume a fixed form of the equation, of the relationship. So for example, like we have here. So in the previous example, this is the data we'll be using, right? So this is the real data, right? This is the true function, the blue one I generated, with some noise, right? So you have this nice curvy landscape. Now, if I assume a linear relationship like I have here, so the true fx is some beta naught, some intercept of this plane, plus then some beta 1, some coefficient times x1, plus coefficient 2 times x2, and so on and so forth, I'm defining a plane in p-dimensional space, right? I'm essentially defining this yellow thing over here. Well, I can do that, of course, and I can try to find that yellow plane that fits this data best. That's a perfectly fine exercise. This is, of course, never going to capture the data really, truly well, right? Because it's just curvy enough. Basically, what this plane will do, it will have a systematic error. No matter how much training data we give it, we will never be able to find the right plane because it doesn't exist. This, as I will show in the next few slides, is called bias. So the model class or the method is right now biased. It will never be able to get to the right model. And the amount of bias is determined by how rigid is this model class. So here, anything that is flat is fine. Anything that is curvy is out of the box. Suppose that we would allow a flat plane with one bump. Well, that's already has a bit less bias, right? It can capture more true functions. However, there's still plenty of bias because if the true data generating mechanism includes 2 bumps, we're already out, right? And so on and so forth. So the rigidity of the assumptions we make here, that's we call bias. We can quantify this, and we'll see this in a few slides. Now, if we do assume that such a form, so in parametric methods, estimating the right f actually is relatively straightforward. It's just a matter of guessing, or hopefully slightly smarter than that, what are these values of b0, b1, and so on and so forth, right? And that's what we can develop methods for. We can think, okay, so if the data would indeed be this flat, right? How could we efficiently find these parameters, and so on and so forth, right? There's entire textbooks written about this. And we'll be studying one of those. Now, this is what I already said. I mean, if the true form f does not match anything in our function class, right? Because this form allows many possible planes, right? But it's simply not there. Yeah, then it's just not there. This is again the true data, right? I mean, definitely not a flat plane. So there's also the option of going non-parametric. Now, non-parametric, we don't have the difficulty of having upfront to come up with, okay, is it a flat plane? Does it have 1 bump? Does it have 2 bumps? I mean, how bumpy is it, right? I mean, what color, what shape, what taste? No, right? We just let the data speak to us. We listen to the data. That's the idea here. We're trying to find the true form of f. That is the goal. Now, as it already pretty much sounds, and intuitively, I mean, your intuition will be right, it will, of course, be much harder to figure out the true form of f rather than just guessing, well, what are the slopes and what is the intercept of a plane, right? Or of some other parametric form, right? Some polynomial, and we just, all the coefficients. That's much easier than also having to figure out, is it a polynomial? Is it exponential? Is it logarithmic? Is it something else? In the end, what we have is that in a non-parametric situation, we have many more parameters to guesstimate, right? In parametric, they're countable. They're explicitly countable. I mean, one parameter, two parameter, many parameters. Here, they're in principle uncountable. In our function class, there's models with almost infinitely or really infinitely many parameters. Now, of course, if we want to fit so many parameters, if there's so much choice, right? We have almost infinitely many possible models. How do we choose the right one, right? There's going to be plenty that are, well, almost all reasonably decent. How do we figure that out? Well, if we don't have a lot of data, lot depends on the problem, right? Typically, it's exponential. You need data points that are exponential in the difficulty of the problem. How difficult is the problem? It's unknowable up front. So the more data, the better. If we don't have enough data, then we run the risk of overfitting, or fitting this irreducible noise, because we can't separate the chaff from the wheat. This is a bit of a problem in parametric. It's also a problem in non-parametric. It is also a problem in parametric, because you can also overfit, but you're much less likely to overfit. You're more likely to underfit, because you are playing the wrong game, right? I mean, you're playing, let's say, you're bringing a rugby ball onto a football pitch. Now, just as an example here, this is what we can do with a smooth nonlinear model, which we'll see then in week 6, yeah, something like that. So 1 or 2 weeks before Christmas. And as you can see, if I just flip-flop between the two, not perfect, but pretty decent, right? The smooth part here is one of the tricks that we use to avoid overfitting, but we can never truly avoid it. You might always just end up in a pickle. Good. Now, about the definition of parametricity, the book goes into more detail, and there might be a question about this in the exam. Who knows? The formal definition is that are the number of parameters in your model class, are they countable? Let me go to the... I love animations, except when I have to go back. Here, are the number of parameters countable? Yes, right? We have p plus 1 parameters. Done, right? Now, of course, there is infinitely many possible values for these parameters, but that doesn't matter, right? There's just a finite number of parameters to be set. Now, suppose that we expand this thing, not just to a linear equation here, but we also include, well, let's say a beta p plus 1 times x1 squared, and a beta p plus 2 times x2 squared, and so on and so forth. We would have a quadratic equation, right? With twice p plus 1 parameters. Is it countable? Yes. This is a much richer function class than just pure linear. Right? I can keep on doing this, right? You know, like a 3rd degree, 4th degree, 5th degree polynomial, right? And the number of parameters starts to grow and grow and grow. And by the time I'm at, let's say, a 1000th degree polynomial, yeah, you better bring a lot of data, otherwise there's no way you can estimate these parameters, right? So that's just an example for overfitting, but we're still parametric. We can still count. There's also, in the non-parametric case, right, on the other end of the extreme, we essentially allow any function. That's how you can interpret it. I can't really give intuitive explanations right now, except for one, perhaps. So I guess, I hope that all of you know what the histogram is, right? Now, a histogram is a member of a non-parametric class of models. Might sound strange, because if I give you some data points, right, and I ask you to come up with a histogram, it's like, okay, well, here's one with 4 bins, right? It's 4 parameters, I mean, easy peasy, or actually 3 parameters. You only need 3 cutoff points. Yes, but no, because I didn't tell you, find me a histogram with 4 bins. I said, the class of histograms. And well, there are histograms with just 1 bin, histograms with 2 bins, with 3 bins, with 4 bins, all the way up to an infinity. So that means that in the family of histograms, that we can't count the number of parameters, right? There is one with well, there's always one with more parameters. Here you don't, right? If you chose linear, you have p plus 1. Quadratic, twice p plus 1, countable. So non-parametricity and parametricity comes down to the countability of parameters. That's the one definition. It's a very rigid definition. how many people often use it in practice is slightly more fluid, you could say, a bit less binary. And essentially, it's about the flexibility. The more flexible the method is, the more wiggly it allows, the more non-parametric we say it is. Or I mean, many people mean it, right? So the more rigid, the more parametric, the more wiggly, the more non-parametric. For example, many people say that a neural network, deep neural network, is non-parametric. Well, technically, this is nonsense. Neural networks in general, yes, just like a histogram, right? 4 bins, sure, can count them. Neural networks in general, yeah, how many layers, how many neurons and whatnot, right? I mean, infinitely many, sure. However, in practice, you choose one neural network, one topology, and you may have 1 billion gazillion parameters. Good luck guesstimating those, but they're definitely countable. So is a neural network now parametric or non-parametric? By the hard definition, it's clearly parametric, but don't tell anybody who believes in deep learning that. Okay? Right, that's it. Okay, good. So, we've been talking about rigidity, flexibility, right? And we have talked about prediction and inference, understandability of the method, right? One of the important ways how to think about this, or to have a picture to keep this in your mind forever, ever after, is this one. We have flexibility on the x-axis and interpretability on the y-axis. And we will be fulfilling this diagram a little bit in the next few seconds. So here at the very top, up over here, I'm so tempted to using my laser pointer, but then Zoom doesn't see it, so try to be inclusive. There, we have subset selection and lasso. You don't know what lasso is yet. I'll tell you later. You also don't really know what subset selection is, but that one is so simple, I can give you the magic almost now. Subset selection is that given a large number of predictors for some target variable y, well, we're trying to find which subset is best. And it might be x1, 2, and 3. It would be x1, x20, and x42, right? Maybe it's just x7, but we try to find the best subset. Now, even if we don't say anything about what is now the relationship between that subset and the output, maybe it's a very squiggly line, it's quite interpretable. I can tell you, these are the variables that matter. All the others, nothing to see there, according to my machine learning method, right, which you should totally trust. So low flexibility, because it can only use that subset, and that's that, but high interpretability. Then we have here on this diagonal a number of other methods. Least squares, or least squares regression. This is what we're going to be talking about in the next 2 weeks. That is actually, I would say, the main driver of almost all of machine learning, whether you admit it or not. Quite interpretable, not very flexible. But as we will see, if you hold it right, it's quite a fierce monster. Then you have trees and generalized additive models. We'll see this towards the end of the lecture. Those are much more flexible, slightly less interpretable. Bagging boosting, not even going to mention this. Near the end, we're going to be talking about support vector machines and neural networks. I position them like this. You can also flip them around, right? I don't want to upset anybody who particularly likes the one over the other, right? This is simply it. Very flexible, interpretability, yeah, okay. Good luck telling what they do. If you want to know where deep neural networks are, my best friends, they're over there, right? I mean, that's, and actually it should be lower, but then you can't see them anymore. Good. Why would we ever prefer a more restricted model if we can have one that is more flexible, that is betterer, right? Well, I'm just rehashing a little bit what I said earlier. I mean, the more parameters you have, the more difficult it gets to estimate all of them correctly, because there's just so many combinations and whatnot, which one is the best. Well, if you read the book, they will still bring the kind of nonsense argument like, oh my God, more parameters, it's more difficult to guesstimate. Yeah, okay, it's 2022, we have GPUs, nobody cares, right? So whenever at an exam, EML or ML, somebody asks why a flexible method's more difficult, if you say computational power, I'm going to subtract a point, right? Formally not allowed to, but I will find a way. Just kidding, but please don't say it. This is not the answer I'm looking for. Complicated models are hard to interpret, which if we want to learn from the data is a bad thing. And if we want to understand why does my machine learning model do what it's do, is also a bad thing. So more flexibility is not always better. And especially if we have few observations, too few, yeah, you're going to be fitting noise. And like I already dropped earlier, how many observations do you need? Well, enough, many. That's pretty much all you can say, except for what I would call toy cases, where you can really define the sample complexity of a model, which is to say you can give formal guarantees that if I want to learn a function of this and this kind, I need at least so and so many observations. These statements you can only make in, well, almost toy settings. Still useful results to have because we know what the limitations are. It's a bit like computational complexity. Right? Any problem of interest in computer science is NP hard. Right? So why do we even bother about computational complexity? Right? I mean, yeah, because it's kind of useful to say, okay, well, can we cheat or can't we cheat? I mean, cheating, I mean, like, if it is not NP hard, then there is a way of computing it more efficiently. Can we figure out how? Right? Can we solve it? Which is not always easy. Good. Then another dichotomy, or actually a trichotomy. We're going to be talking in this course a very, very large part about supervised learning. Much to my, well, not annoyance, but I mean sadness, because I'm really an unsupervised learning person. I want the data, I want to learn from the data. I don't want to just, anyway, this course you could almost call elements of supervised machine learning. And yet here I am. Because yes, you need to know about this. This is really the workhorse. The setup, we already discussed, we have input, output, and we want to just teach or train, find that function. There's also a class of machine learning, which we're not going to discuss, sorry, called semi-supervised learning. But I just wanted to highlight that it exists because it's cool. Why is it cool? We only get a few supervised examples, and we get a ton of unsupervised ones. So for a few where we have both X and Y, and a whole batch where we only have X. And the interesting thing is that if we do our homework well, then we can actually get a better prediction system by taking into account the unlabeled X's rather than just looking at the labeled ones. Because we get a better estimate of how does the X world look like. We can estimate the density, the probability distribution, the function behind X better. It's a very cool class of methods, but it really goes far beyond what we can discuss here. So, nope, sorry. Unsupervised learning, we're going to be dabbling in this only 2 lectures out of 14, which really means my heart bleeds. But trust me, I've been trying to rework the course, and then I just found like a reality called I should really be teaching unsupervised first. The idea here is we have input, no output. Tell me about the data. Tell me something I don't know. What should I know about the data generating process? In my experience, almost all problems worth solving in machine learning are in the bottom one. And yet I'm only going to spend 2 lectures on it. Hate on me if you wish. Just 1 or 2 examples of this. So here we have some data, and the task is find clusters. What are clusters? Clusters are points that, well, belong together or seem to belong together. Here they're quite well separated, right? So I think if I would ask anybody, they would say 3, right? Or plus or minus 1 maybe. And indeed, if I color them, this is how I generated it. In practice, data looks often like this. Well, how many clusters do we have? It's still 3, but good luck finding them, right? I mean, they're much more hidden, and they can easily make it much, much harder, of course, because they're now all of the same size, they're of the same density, and they're just in 2 dimensions, and it really can become much, much harder. This is what you would like to find. So overall, how do we now say if some model, we're now back in supervised land, so forget about clustering, if it's good or bad? One of the main methods we'll be using is the so-called mean squared error, MSE. And in the first half of the course, we're going to play pretend that we're a little bit stupid. We only have training data, and that's that. Right? Only later we have test data, and we can look at generalization error. But the first part, we're stupid. It's fine. We're all stupid, not just you, just me too. How do we compute the MSE? MSE is simple. We sum over every training example that we have. We look at how far off is our predicted value from the true one. We take the square of it. We normalize. So it's the average error, right? That's basically how you can think of it. mean squared error, or average squared error. In the end, only, well, beyond halfway the course, we're actually interested in, okay, how well does our function do on unseen data, right? How does it generalize? Does it fly for real? It means we want to estimate the average squared error between, well, unseen points, which we call x0. x0 we don't have in our training data. In our training data, we only have x1 up till n. So we're going to test error, or generalization error. So back to actually, I really wonder why on earth were the inference and the clustering slides here. I don't know. PowerPoint is sometimes interesting. Maybe they got moved around unwittingly. Good. Here we have, we're talking again about flexibility and overfitting. So picking up noise that you don't want to. Left-hand side, I generated some data, which is almost linear. So the true function is the black line, as you can see, right? So it's a little bit curvy, not so much. And then we show 3 different methods. A linear model, that's the yellow line, smooth splines, and rugged splines, which we'll see later in the course. As you can see, the rugged splines are, well, stupid splines, right? So they are way too wiggly for their own good on this data. And what we can now look at, if we project this over the flexibility of the method, how many degrees of freedom does it have? How wiggly can they be? Then we see that, well, the yellow one, linear model, has a very low flexibility, right? So essentially, we can only change the slope and the intercept, and that's that. Then the blue one, the smooth splines, well, a bit more wiggly, but not so much. And well, the green ones, yeah, very wiggly. What do we get? That the training error, the one that we can measure on the training data, the MSE, as you can see, the green one clearly wins. But just for looking at the picture, you'll see, okay, this is going to be a bad generalizer. And indeed, if we do measure the test error, because I know the generator of this data, I can evaluate this, it's indeed bad. So that raises the question, how can I, without knowing the true red line, how can I choose which one is best? And when is it best? This was almost linear data. I mean, do you have something a bit more nonlinear? Yes, I do. So this is more cubic, right? I mean, I think I recall correctly. So true function is black. Slightly different curve. You can see that still, in this case, the smooth splines are best, right? They're closest to the two. But the green one, well, there's a big discrepancy between the two, but even though you might think it's much better than the blue one, in practice it's a little bit worse, but it's still better than the yellow one. So, but these are the values, the grain line are the values that you have, right? So this is the difficulty in machine learning. On training data, it's very difficult to say, like, well, something looks great, but not all that glitters is gold. That's basically what this comes down to. Let's go to highly nonlinear data. Okay, I'll change the title when I get to it. So, very nonlinear. The yellow line, really bad. It really underfits. The blue one, still pretty decent. And the green one, actually too. So the flexibility of a method really comes to shine when, well, the true function is also very flexible. That is something to, do you know this beforehand? No. Well, this is then tricky. Can't really give you a proper solution. Now this trade-off that we see, this flexibility and the mean squared error, how it performs in practice, we can quantify this, we can formalize this. And that is, now we come to the title of this lecture, bias and variance. I already explained what bias is. Bias is this rigidity, right? The mismatch between the true function, well, what we would like to get a fingernail behind, and what we slap on it, right? Flat plane, very rigid, right? Or very rigid, sorry. So high bias. Only works well when the truth is also flat. Now, what is then the variance? So let's break down the expected error again. So the MSE, the expectation mean squared error that we have over here. And we can break this down. And given that we are still defining the first homework, I cannot say for certain if there's going to be a question on this. It just smiles. I'm not sure what that means. Maybe, maybe not. We'll see, we'll see. We can break it down in what is the variance over unseen points of the predictor. The bias of the predictor squared plus the variance in the noise. Variance in the noise, this is the irreducible error, right? We will never be able to fix this, right? And so that's always there, always part of the error. Too bad, right? And we can break this down. Why and how we can break this down, there might well be an assignment about this. Otherwise, it will be discussed in the tutorial in a bit more detail than I do here. What is the definition? Well, the bias and expectation between these here, up, there we have it. Systematic deviation, already explained this. The variance, what is the interpretation there? The variance you can interpret like this. Suppose that I, in the previous examples, but then in the one where it's been really bad, think of the green line here. Think of the green line, right? It's overdoing it, right? It's a bit overeager. Now suppose that I, rather than this data, I create a new data sample. Same number of points, right? I sample a new batch of data points. And I fit again a green line. How similar or how different is this green line going to be? Probably quite different, right? How similar and how different is the yellow line going to be? Probably very similar, right? Green line will wiggle a lot, not just here, but also over different data sets. The yellow line, easy peasy, everything is calm, right? Hence, for the green one, it has a low bias because it can fit, in theory, anything, but it has a very high variance. It's very sensitive to the training data. The yellow line has a very high bias. It can only fit things that are aligned, right? But it has a very low variance. Given different training samples, it will be relatively stable, right? And those are the two key components that make up if a method works or doesn't work. So if you start with a straight line, right, the high bias, low variance, then and you see it doesn't work so well, okay, then we need to increase or we need to decrease the bias. And now we come to the bias variance trade-off. We cannot decrease the bias without increasing the variance, because we're making things more wiggly, and by making it more wiggly, it becomes more sensitive to the data points we have. So in the end, we want a method that doesn't have too much of a bias, but is also not too high variance. That's what we want to keep in balance, right? And that's why we all still have a job in machine learning land, because that is the difficulty. And there's a lot of things to be still seen there. So bias, the expected error between, well, the true one and the predicted one, systematic. The variance over the predicted one is the squared over the, so the difference between the true one and the expectation of the true one over different data sets. So just, what is this useful for, right? This is not just something on paper. It's really something how you can analyze methods. And in a way, this lecture right now, and this part about bias and variance, is the most important part of the entire course. I don't think it's smart to right now call it, well, a day, see you at the exam, right? There's still a lot more to be told, but this bias variance, this balance, this trade-off, we will see it again and again and again and again until you're sick and tired of it. And then a bit after, it's like, okay, but wait a second, yes, this is really important. And then I have succeeded, or Alexander, I don't know when this moment comes. So what we have here, we have three settings: moderately nonlinear, almost linear, and highly nonlinear. And then for a specific model, it makes some errors, right? So the MSE that we see is the red line. This is the error that it makes. Zoop, zoop, and zoop, those over here. And we can break this down, this error, into the bias part and the variance part. So if we allow very little flexibility, we have a model with very high bias, right? It's very little flexibility, right? Very rigid, high bias. So look, the error is for a large part made up by the bias, the green one. The higher we bring the flexibility, the more wiggly we allow it to be, you see that the bias goes down because it can now fit the true moderately nonlinear function, right? Quite easily. It only has like 5-6 degrees of freedom, but then it starts to overfit. That's basically what we're seeing, right? The variance part is where overfitting is, the proneness to overfitting. Right? Rigidity versus proneness to overfitting, bias and variance. For almost linear, well, we need a method with only very little flexibility. If we give it too much, there is nothing to be gained on the bias front, but on the variance front, there is a lot to be lost. So be careful. On the highly nonlinear, yeah, if we start with a very rigid function, almost all of the error is made up by the bias, right? Because we are so far away from the truth. So only if we increase the flexibility sufficiently till 10 degrees of freedom, then finally we can grab the function by its tail. And as you can see, if we now go up, it only starts here a little bit, right? Then the variance starts to go up. So how to choose between bias and variance? This is a major topic between choosing between different models. And hence this comes down to model class or model selection, which we'll see somewhere around lecture 6 or 7. Good. This was for regression, right, where we want to predict a certain value, so it makes a 0.5, 0.6. How about classification? How about, back to the example of Professor Rahman, right? I mean, he wants to predict, okay, let's say, well, based on his genes, is he awesome, yes or no? Something like this, right? I don't know him personally, so I am a very unbiased classifier. But the task of saying like a yes, no, or like really like a nominal type of decision, right? It's this category or the categorical. That's what classification is about. How do we measure performance there? Well, we can't really do like a squared of the error so much, right? Either you get it right or you get it wrong, you take a square, and yeah, what is that? So instead, we use the misclassification error. We essentially simply count how many errors do you make on average. This we also call a loss function. There's many different possible loss functions, right? Misclassification error is one of the standard ones. The book might say the most popular one, maybe once upon a time, but for us right now, for the next semester, it is, right? It's super popular. It's essentially defined as over each data points, we take the average, we take an indicator function I, and I is only one if you make an error, right? If the predicted value Y is different from the true one. And we just sum them up, normalize, there we are. That's the average. In the end, the test error over unseen, we again want to just have an average. Now, that allows us, actually need to think a little bit. Yeah, okay, I'm going to continue for 5 more minutes. I mean, unless you really want to go, then you have my permission. But 5 more minutes. Because then I'll go a little bit further than I plan to go, but that is fine. So we now have some error, right? I mean, that, how can we minimize this? Well, actually, I can tell you a secret. We know the perfect classifier. This is the perfect classifier. It's the Bayes classifier. And the Bayes classifier, I mean, there's no improving over it. This is really the best one. What does it do? It assigns that class, J, right? So it looks over all possible classes, class labels, right? I mean, awesome, yes or no, or is it red, blue, or green, whatever categorical labels you have. That maximizes this probability. The probability of the label given the input. This is the best one. You can't beat this one. Now, and why is it called Bayes? Because Bayesian statistics and whatnot, when we can flip around prior and posterior and whatnot. This is amazing if we have the true distribution, if we have our hands on this PR. If we know this, there's nothing that can beat it. And on synthetic data, I have it because I generate the data and I can compute this. In real data, I don't have it. And we can at best estimate it, and then this becomes very tricky. This is just as hard as anything else. However, on synthetic data, I can compute it. And that allows me to evaluate how flexible or how biased, how variant are different classifying models. And that's useful for today's topic. For example, here we have a task of binary classification. So here I have blue points and I have yellow points. And the task is that if I give you a point, you have to say blue or yellow. Right? That's the task. Now, this is not an easy task because, as you can see, the stupid yellow points, they invade the blue ones over here and vice versa. So the problem is not what we call linearly separable. You can't draw a line that really separates things. It's nonlinear. This dashed line shows the decision boundary that if you would have the original distribution that generated the data, and it indicates those points in the space where it's really 50-50. Where you're really like, okay, is it yellow, is it blue, or is it which color has the dress, right? It's really like in the middle, That's basically, well, and everything that where the one probability is a bit higher than the other, there you say blue, respectively yellow, that's that. Okay, this is nice. Now, we can also use this to define the irreducible error. Pretty straightforward. It's just basically what is then the maximum. Basically these points here, I mean, there's no way that we should be able to, the yellow ones over here, we shouldn't be able to get them right. Just like these blue ones, too bad, right? I mean, they're just casualties. I mean, not, in this case, we can compute the base error rate as 0.13. Okay, now I'm going to tell you what is one of the methods that every machine learner, every data miner loves to hate. It's called nearest neighbors. You can do nearest neighbor classification, and also the variant for clustering, but let's stick with nearest neighbors. Nearest neighbors is one of the simplest methods that you can imagine. Namely, if I want to know, for this point over here, what is the value, right? Is this red or is this yellow? Or is this blue or is it red? Yeah, is it red? Yeah. Okay, this was clearly, I was looking at the pointer and it was red. No, is it blue or is it yellow? Well, and if you don't have the true distribution, right? I mean, well, what would your guess be? Probably you would also guess, well, blue. And I would ask why? Well, there's quite a few blue points close by, right? Especially if I would have asked something here, then you definitely have said blue, right? And here you would have said yellow. And here you would have said, yeah, I don't really know. K-nearest neighbors formalizes this to the point where you simply, for a query point, it's the x0 that I just highlighted, you look at the k nearest points. So basically you draw a ball around it and until you have k points within that, and then you choose the majority among them. Now, if you're given that you want to choose a majority, it helps if you choose k as an odd number, right? Otherwise, you have to deal with ties and who likes those, right? So typically you use 3, 5, 9, and so on and so forth. Here we have the boundary. So we have to base the boundary, that's still the dashed one. The black boundary is the k nearest neighbor where we look at the single nearest neighbor. Okay, just as an intuition and to see if like some people are still awake. K nearest neighbor with k set to 1. Is this a classifier with a high or low bias? And then similarly with a high or low variance? Anybody? And I promise I don't point. I will also not point and laugh. Sasha. Low bias? Why? Exactly. It's super sensitive, right? By just adding one more point, all of a sudden in a giant area, I can change the decision massively. It's a very high variance. And it is indeed very sensitive to the data. It's very flexible, right? It just looks locally. So yeah, low bias, high variance. Typically those go hand in hand. Now, let's look at this. Next slide has a lot of points, so it might take a few seconds to load. Yeah, there we are. So I drew this a few years ago by hand. And this is really like all those points, right? I mean, they're all, because I didn't like using just a snapshot from the book. This is, sometimes the OCD gets the better of. Anyway, what do we have here? We have k nearest neighbors with 1 that we already saw, and well, we didn't draw the conclusion, but let me ask Sasha, is this one, does it feel right, or does it feel overtrained? Overtrained? Very good. On the right-hand side, I set k to 100, even though I have, well, not many more points. Do you see, it starts to basically form like a linear line between it, and that's that, right? It gets a very high bias, because sort of like the average line, that's what it is. So low variance, because if I now add a point, this line is not going to change massively, right? It's just 1 out of 100, it's barely an influence. Low variance, high bias. High variance, low bias. And in the middle, with k is 10, and again, I just said, don't choose k at an even number, but in the book, they don't listen to me. There you see that you get it about right. Well, this slide does not mean that you should always use k as 10. That really depends on your problem, but good. Final slide. Here we have an overview for this particular data set, if I don't mess up. But we have the base error rate. We have the misclassification error on the training set. That's the green line, right? And we have the test error. And what we have then, so rather than drawing this from k is 1 here and then blah, 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 all the way to n, we do it by a ratio, 1 over k. It always confuses me, so I added for myself that 100 in this case is k is 1, or 1 is k is 1, and then here this is over 100. And as you can see, the higher we make k, we get a worse training error. But if we look at this curve here, this is, well, not quite U-shaped, but in this area, well, we get a classifier that is spot on or very close to the base error rate. That is good, because we can't do any better, right? That we just learned. So in the remainder of this course, we're going to see KNN again and a whole bunch of other methods. But what the main point is and why this bias and variance is so ridiculously important, we want to, in the end, find models of this kind that are in this dip, that perform spot on, that are not too complicated, that are not too simple, that don't have a too high a bias, that don't have too high a variance. And how to figure this out and how to navigate this, yeah, that is essentially what this entire course is about. So on that bombshell, I want to say thank you very much for your attention. Looking forward to seeing you next week. One very last announcement. I just remembered. Sorry. There is currently in the schedule a tutorial planned on Monday. But Monday is a bit of a stupid day because Tuesday is a holiday. That's both for us as well as for you. So I'm not sure if everybody's going to be here, wants to be here. So what we're going to do is the following. There is going to be a tutorial for those of you who want it. There's going to be a recap of this lecture, if you want it. And if you have any trouble setting up the assignments, it's going to be there, right? Both online and in person in lecture hall 1 or 2. I don't know at the top of my head. The week after, then we get properly started. Yeah? Okay, good. That's what I wanted to say.